In this paper, they explain how to take already pre-trained model, and on inference time, they reduce the precision of these matrices key query value, and that makes it a lot faster to calculate, to do math moves, and so they accelerate this inference time without sacrificing performance or the performance loss being negligible. They achieve 2.1x speedup compared to FlashAttention 2. So I would say I am at level 3 of understanding this paper, so I understand methodology, proofs, code, etc. There is only one or two parts that I didn't understand, and I will tell you when we get to them. But this video will help you accelerate the process of understanding this paper a lot. They start by explaining that in attention mechanism there is n-square scaling. So each token needs to attend to every other token. So if we have a long context window, long sequence of tokens, this becomes the primary time consuming component of the transformer. And then existing quantization methods primarily focus on optimizing the linear layer. But their new method, SageAttention, focuses on quantization of attention. The operations per second of our approach outperforms FlashAttention 2 and xFormers by 2.1 and 2.7% respectively, and it also achieves superior accuracy performance over FlashAttention 3. They tested it on a lot of models, and there is almost no worsening of the performance. The performance is almost the same. The code is available on GitHub, and let's take a look. I'm gonna zoom in so you can see the pictures better here. So FlashAttention 2 and SageAttention, their method, we get 2x kernel speed, and we get also 1.3x lower end-to-end time. I cannot notice any difference between these images. I think you cannot either. So as they explain, there is almost no difference. Let's take a look at these two other photos. So this is latency of attention. So here we can see three lines. One is attention, one is linear layer, and other components of the transformer. And as we increase the sequence length, we see that attention takes exponentially more time because each token needs to attend to every other token. So this is what they are trying to address with their new quantization method. Then they also say that other quantization methods primarily focus on the linear layer, but here they apply the quantization methods onto the attention mechanism. So here they directly quantize these matrices into int8, and we see that this image gets very blurry. Then they use FlashAttention 3 on attention mechanism, and the image is not much better. And then there's SageAttention. There is almost no difference. Then they say because attention is a lot more complex mechanism than linear layer, linear transformation, just applying the quantization to these matrices naively. So query key value and P matrix, if you don't know, is when you calculate all of this softmax of all of this stuff, this is P matrix. So this will result in a significant degradation of the performance across various models. So they tested image models and Llama 2, and I believe they also tested more models. They identified two main challenges with quantization of the attention mechanism. The first challenge has to do with the key matrix. It creates outliers in the key matrix when we try to use 8-bit quantization, for example. So some values are a lot higher or lower than other values, and this difference causes big errors and big differences in further calculations. And the same thing goes for projection and value matrix. So they get changed so much that now their product is so much different and there is a big loss of performance. So in my understanding, the main problem is when you reduce the accuracy. This may not be a big deal for linear layers, but because there are so many complex calculations here and matrix multiplications, this is a big problem for the attention mechanism. The errors add up to each other, and then in the end there are big errors. Then they propose SageAttention method to solve this problem. This is a post-training quantization method, which means that you can simply replace the original high-precision implementation on the inference time after the training. So you don't need to train on this method. We propose several techniques to achieve this goal. First, we opt in to quantize the tensors in attention to int8 rather than floating point 8. This decision is based on the fact that int8 math mul on some commonly used GPUs like these ones are 4 times faster than floating point 16 and 2 times faster than floating point 8. Moreover, int8 quantization of matrices Q and K is more precise than floating point 8 in attention. To address challenge 1, we propose a method to smooth the K matrix. This method significantly enhances accuracy with a negligible time overhead, less than 0.2%. And then to address the second challenge, they keep P and V matrices in F16. Now it's a bit unclear if they were reduced to FP16 from like FP32 or they were trained like this from the beginning. And instead of reducing these two matrices, they use low precision FP16 accumulator, which from my understanding, when you are doing the matrix multiplications, so you're adding, multiplying elements between each other, then you use a lower precision for those intermediary results. This strategy doubles MathMul's speed without sacrificing any accuracy, and then they try a bunch of different similar methods, and they show you how to choose the best one for your case. They implemented this into code to work well on these two GPUs, RTX 4090 and 3090, and they are using or implementing rope with quantization and a fast self-attention kernel inspired by FlashAttention style tiling. We discussed the performance already, you can find it in the GitHub. To understand this method, we need to first understand FlashAttention and dynamic quantization. So let's start with FlashAttention. The main problem FlashAttention is trying to solve is the following. As I explained, you have n-square scaling. So if you have a long sequence length, these matrices are going to be huge. So it's very slow to write those matrices into memory and read them from the memory. During the calculations, they need to be written and read many times. FlashAttention is trying to work around that, so they have to be written and read fewer times. So when you have n by n matrix, you need to apply masking to that matrix, softmax, and dropout if you are applying them. So you need to apply all of those things separately to a huge matrix. I'm gonna show you a screenshot of this video of FlashAttention explained. You can find it on YouTube. So here we have PyTorch in the implementation of attention. You have MathMul, masking, softmax, dropout, MathMul again. Each of them takes time separately, and then FlashAttention is fusing everything together, so they call it fused kernel, all of these operations, and it takes a lot less time. First, they explain how this self-attention mechanism works. I think you know that, but let's quickly remind ourselves. So first we get this scale dot product. So query times k transposed over this square root of this dimension. Then we calculate softmax of that scale dot product, and then we get the output by calculating the softmax matrix with the values matrix. The matrices query, key, and value each have dimensions n times d. So n is sequence length, number of tokens, the context window, and d is the dimension of each vector embedding, and d is usually very small, while n can be thousands, even millions. While the matrix SP are n times n, so this is where you can see like these matrices are going to be huge, because this can be like million times million. So therefore S and P matrices suffer from huge amount of memory reads and writes. FlashAttention proposes a new method where they split query, key, and value into blocks, and they call them QI, KI, and VI, and they have sizes of BQ. So I clicked something anyways. So the size of the block of query matrix is BQ. As you can see, this has only one dimension, and then BKV and BKV, both the same matrices for query blocks of keys and values. Now I think this means that they are the exact same matrix, not just that they have same dimensions, but I'm not sure. Let's see further what they say. Then to avoid the memory input output for S and P, it uses online softmax to progressively compute each block of output, for example OI. So now I am also struggling to understand this part, but let's start with this sentence. Mij and Lij are bq times 1 vectors, which are initialized to -infinity and 0 respectively. And then this guy, this sigma with this little hat, is an online softmax operator. And what it does is it helps to iteratively, part by part, calculate a softmax function without having to write everything into memory and calculate everything at once. So as new data comes in, this iteratively, gradually gets updated. Yeah, but this part is kind of tough for me. So maybe I'll go into FlashAttention more deeply in a different video, or you could check YouTube to find different videos about explaining this mathematics. And then dynamic quantization is a lot simpler. So let's say we have some matrix A, and this psi of A represents a quantization function that turns this matrix from a higher precision matrix into a lower precision matrix. And so we're gonna get this lower precision matrix, for example, int8 matrix from this, for example, this can be float 64 matrix. And we're also gonna get this scaling factor, in this case delta A, that's gonna let us convert back this small precision matrix into this high precision matrix. But since it will not be perfect, it should be like as close as possible. For example, we see that we convert this into a smaller precision matrix, and then matrix B we convert into a smaller precision as well. Then we multiply those two smaller precision matrices to get the C small precision matrix. And then we use the same psi function, just inverse, and with these two scaling factors to convert it back into the high precision matrix. And now in their method SageAttention, they combine these two methods. So first they quantize them. So they convert Q, K, P, and V matrices into lower precision matrices. And then they apply this FlashAttention method to them. So these smaller matrices are still the chunked out blocks. So this is not a full matrix, this is a block of the query matrix. And they do this for each block separately. And then they calculate the softmax. And they say here online softmax is left in full precision. Here you can see below what's very important is this K matrix. You see how K is very separated by channels. So if you directly apply 8-bit quantization here, this will make things even worse, and there will be big outliers, and the difference between these channels will be too big, and there will be big errors. So they are going to change K matrix a bit differently. So you see that this sign is a bit different here. They're using phi, and this is psi, I think. Yeah. Directly quantizing QK often results in large error. Particularly quantizing QK to int8 yields completely blurry image video in text to image video tasks. But here is the thing here. Each token here has a large shared bias and a small variation in signal. So the problem is not that the signal unique signal between tokens is different. It's just that this shared same bias is different. It's large. So what they do here is they take the average, the mean of all of these channels, all of these tokens, and then they subtract that mean from each of these channels. So that's how they smooth it out. And I'm gonna scroll down to show you this formula. So this gamma of K, this is the smoothed out version of the K matrix. So they say K minus mean, the average of the K. And so there is no such large variations between different channels. There are no such large outliers. And one interesting thing is this is the proof that when you subtract a constant from this function before you apply softmax to it, it does not change the results of the softmax. So if you subtract this constant, the mean, then that is the softmax probabilities will remain the same. In other words, a full precision K is subtracted with the mean before eventually being quantized. In this table, they show the difference between smoothing K and not smoothing K for all of these different quantization methods. So they explained how these methods work in this paper. There is some mathematics involved, so you can see that when you smooth k, score is better for cog video. For this one, score is better here, score is better here. So basically it seems like every single time score is better if you smooth out the k. Now let's take a look into this table, average accuracy using different data types across all layers of real models. So if we use int8 quantization for q and k matrices, and we use E4M3, which is 1 sign bit, 4 exponent bits, and 3 bits of mantissa, then those show the best results. So this is cosine similarity of the expected value to the given value that model produced, and then relative error. I think this is, I don't know why this is called, I think this is like absolute error, and then this is standard deviation. Then this combination is best, then this one, and then, but you can also see that, for example, this combination and this combination gives the same result as this combination. This table shows worst accuracy using different data types, but this is a bit confusing because they marked in green the best results for some reason, because that's how I see this. This is the best result, this is the best cosine similarity, this is the smallest relative L1 and smallest root mean square error. So the worst one would be, for example, this one combined with this one for cosine similarity. Let's talk about these quantizer types, but this is a bit dense, so I got a better version here. So original values are divided by the scale factor for quantization and multiplied by it for dequantization. So there is this concept of a scale factor. Per tensor quantizer idea, use a single scale factor for the entire tensor, matrix, or multidimensional array. Why? Simplest approach, computationally efficient. And then scale factor here is a single number that represents the range of values in the entire tensor. How it works, find the maximum absolute value in the tensor, uses it to compute a scale that maps the values to the target range. For example, this range, or for example, this range for int8. So it's fast, low memory overhead, and may lose precision for tensors with wide range of values. Then we got per token quantizer. Assign a separate scale factor to each token, typically a row or a column in the tensor. Better preserves precision for tensors where different parts have significantly different value ranges. Scale factor here is a set of numbers, one for each token. How it works, computes a separate scale for each token based on its maximum absolute value. And then pros, better precision than per token for very varied data. Cons, more memory overhead for storing multiple scales. Per channel quantizer, assign a scale factor for each channel of the tensor. Useful in neural networks where different channels represent different features or types of information. What are channels? In the context of neural networks, channels often refer to different feature maps or dimensions that capture various aspects of the input data. For example, in image processing, you might have separate channels for red, green, blue color information. Scale factor, a set of numbers, one for each channel. How it works, computes a scale for each channel based on its maximum value. Pros, preserves precision across different types of features. Cons, more complex than per tensor, but less overhead than per token. Then we got per block quantizer. Assign a scale factor for blocks of tokens. Balances precision and efficiency, especially useful in attention mechanisms where data is processed in blocks. Scale factor is a set of numbers, one for each block of data. How it works, divides the tensor into blocks, for example submatrices, and computes a scale for each block. Pros, good trade-off between precision and computational memory efficiency. Cons, more complex to implement than simpler methods. So all of that is explained here, but this is a bit math heavier. So here they say like which methods they picked. So quantization granularity for Q and K. They are picking per token, per block, and per tensor, and then per channel is not possible, not feasible. And then for data types of Q and K, they are picking int8 because those are best in the table that I just showed. and then quantization granularity for P and V matrices. So they're gonna take per block for P matrix and per channel for V matrix. Then data type for P and V, they're gonna choose int 8 because it's a lot faster, even though it might have a bit smaller accuracy as we saw in the table. And these are accuracy metrics that I just explained. So they use cosine similarity, relative L1, and RMSE. Below that there is a subtitle FP16 accumulator, much more accurate and efficient solution. They say that using int8 is very poor in some model layers. So they propose to use FP16 as data type of matmul PV with a FP16 accumulator. Now let's explain the algorithm. So we're gonna look into this right box, SageAttention B, and that algorithm is implemented here. So first we can see this Q matrix here, and it's split into these two parts. So they call these stream processors. So this is, I believe these stream processors are literally memory spaces where these parts are written. And these parts will be processed parallelly inside of stream processors, so inside of memory. So we quantize the Q matrix, and then we also split it into blocks. And while quantizing it, we also get this scaling factor here. So we're gonna use this to later convert the quantized version into full precision version. We're going to follow the same algorithm here in the pseudocode. Now this is a bit confusing because they mark this as FP32 and they mark here Q as FP16. So I'm not really sure what's happening here, but I think it's not so important because here they also have these matrices, and then we have some block size for splitting them into smaller blocks. And then in pre-processing, they subtract the mean value across tokens of k, so they smooth out the k as we discussed earlier. And here you can see k. So after they smooth out the k, they have quantization. So they quantize q, but they use this scaling factor over square root of d. They quantize k as well. So they use int8 per block quantization for these ones. Then they divide q quantized into n over p cube blocks, and then they get q quantized, and then I is iterator for each block. And they also divide k quantized and v that is not quantized into n over b kv blocks. So kv is the dimension, and they get k quantized I and vi. Yeah. And then they make a loop for I in 1 to tm do. So this is parallel that in stream processor, so this is executing parallelly, and I'm pretty sure it's executing parallelly for each block with iterator I. And then we load this block for q, and we load the scaling factor for this particular block as well, so we can scale it back. And then for j in 1 to tn do, so tm is dimension for q, and tn is dimension for k and v. So here we load ki, vi, and the scaling factor of k into the sm, and then we calculate this s, which is a matmul, the classic matmul. So we matmul q and k but quantized blocks, and then we scale them back into full precision. So this part below is FlashAttention, which I said was a bit tough for me, but basically this m is gonna keep the maximum value from the previous one, and the current one, this row max, I'm not really sure what this means, sorry. And then this is the softmax, and then the rest of this is just the rest of the FlashAttention. And then after we calculate the output, we're gonna combine all of the outputs of all of the parallel executions into the final output for this attention layer. If we go up a little bit, we can see the same thing drawn here. So here we calculate this S is basically Q, quantized and blocked Q, times K, it's a matrix multiplication, and then scaling them back, and then online softmax, and then we convert back to FP16, and then accumulate one by one all of the blocks into FP16 into this output. So this P times green thing is the values. Below that they explain some performance tricks. So they do this quantization and stuff and blocking before the attention. So for example, in this case, they do it in rope embeddings. So rotary position embeddings, this is when you convert tokens into these embeddings. So at the same time, before writing it to the global memory, they also do the quantization and scaling and stuff. Performance analysis. If you're using int8 matrix multiplication, current mainstream hardware can achieve 2 to 4x throughput. Then FP16 on edge accelerators such as RTX 4090 can still achieve a 2x improvement over FP34 accumulators. Then also there is quantization overhead. So converting quantizing and dequantizing, this is a decent overhead. But if they combine it with rope, then they can avoid input-output overhead of quantization. But they still need to calculate it, so just they can avoid writing it into memory. So experiments main result, the speed of SageAttention is approximately 2.1 times faster than FlashAttention 2. Furthermore, SageAttention achieves an average real speedup of 2.83x compared to the original attention in various models, with negligible loss in end-to-end metrics, that means benchmarks, or the performance of the model generally. So the experiments they've done, this is a big blob of text, but I have it better written here. So the models, Llama 270B for text generation, CogVideoX for text to video generation, Undiffuser for text to image, and TIM for image classification. Datasets used, Wikitext, Lambda, and MMLU for Llama 2, and then open-ended prompt sets, and you can check this out as well. So the metrics, perplexity and accuracy for Llama 2, and these metrics here for these other models. So now we have a bunch of these graphs. So what they show is a graphics card. So this is one graphics card, it's same here, and then this is different graphics card. Then they also differ in head dimensions, so 64 and 128, and causality, causal false, causal true. So causal means if it's able to see the following tokens. So for example, in autoregressive models like ChatGPT, it would not be able to see the following tokens and generating the next token. Here we can see torch. It's very small here. This is tera operations per second. The speed of torch is very small. Then we see FlashAttention 2, which is the gray one, and then darker one is xFormers. So FlashAttention 2 outperforms these two, but then SageAttention outperforms all of the other ones consistently. So you can scroll through this. This is basically very similar. It just these couple of metrics changing as I explained. So the graphics card, head dimension, causal, etc. So basically their method outperforms consistently every other method. And I think take a look at how much it outperforms when the sequence length increases. So torch here is really diminishing, starting to disappear, while SageAttention is staying very consistent and even improving the speed. In the table below they show speed. So these are the models again, and then we have shapes of QKV, and then we have original attention speed in tera operations per second, and then SageAttention is like 2x higher, and here it's like almost 6x higher. But this is because it's using a torch here, so I'm guessing like there is no FlashAttention, doesn't work for this one. And here we can see the loss. So SageAttention has a bit more loss than full precision, but only a little bit more. You see how only like one digit here. So there is no loss here, it seems. That is, this accuracy is almost the same. Then for this model, I think there is only like there is almost no loss. Maybe there is a bit of loss here. And these arrows mean lower better, higher better. So here this is lower than this, so this is a bit better. But this is full precision and this is SageAttention. So let me scroll through these tables as well. So this is they're different algorithms. These are the tables that we showed already with just different algorithms, so you can see these algorithms here as well. They also got some benefits of adaptive quantization, so they have two algorithms that they compare, the simple one and like this one that's doing adaptive quantization, and they see that results indicate that the adaptive strategy increases the speed of attention by 11.7% without any loss in the metrics. Future work will leave the implementation in Hopper architecture for future work, so they want you to implement this into Hopper, which is expensive NVIDIA strong cards with this architecture, and FlashAttention 3 is implemented for this architecture and is very fast. Thank you for watching. Some of this mathematics was tough to explain, especially in FlashAttention. So I'm gonna keep making these videos. See you next time.